Everyone, my name is Regen Libreta and I'll be your 44th in Group 3 and right now I'll be discussing to you the sub-remaining topics. Precipitation data analysis, estimation of missing data. Estimating the missing data and adjustment of records. For frequency analysis of the missing data, a long record is required. So, why it is very important to estimating the missing data? Let's say, for example, in the infrastructure design or engineering field, engineering projects like dams, drainage system, and urban planning rely on historical precipitation data. Estimating missing values ensures the safety and the cost-effective design. And in climate studies, long-term precipitation rewards are essentials for identifying trends and patterns in climate change. Estimating missing data helps preserve the continuity of data sets for accurate climate change. So we have the three methods to estimate or estimating the missing data. We have the station year method, normal ratio method, and double mass method. So, station year method, the missing record at a station in particular year may be found by a ratio and average or by graphical comparison. So, the station year method, we have the two or more stations that are combined into a one long record. So, example, and a weather station has complete data for 10 years, so it means to contribute, we have the 10 station year. And in this station year method, we will be using the ratio proportion method to find the missing data. So we have the example. In a certain year, the total rainfall of station A is 75 centimeter, and for the neighboring station B, there is no record. But if the record at A and B are 70 and 80 centimeters respectively, the missing year's rainfall at B, say the precipitation B can be found by simple proportion as. So it means that in the station B, we have the missing data. So we'll be using the ratio proportion to find the missing data. We have the 75 all over the 70 at the station A equals to the precipitation B, which is our missing data, and all over the 80 at the station B. So we have the 85.7 centimeter. So next is the normal ratio method. In this method, simply ratio and proportion process and get the average. So we have the formula Px is equal to 1 over n, which is our n is the total number of the nervous stations, and the multiplied by the nx all over the ni multiplied by pi. So where our px is the missing precipitation at station x, and nx is the normal average annual precipitation at station x, and the ni is the normal average annual precipitation at nervous station I, and pi is the recorded precipitation at nervous station I during the same period, and n, which is our total number of nervous station. So we have the example. Let's say the missing precipitation at station A needs to be estimated, and we have the following data. At station B, C, and D, we have the normal precipitation and recorded precipitation. And it says here that the normal precipitation for station A, which is our NX, is 110 centimeter. By the using formula, we'll get our precipitation, record precipitation in the station A that we need to estimate, which is our missing precipitation. So, 1 over 3, which is we have the 3 station, multiplied 1 over 10, which is our NX, all over the NI, and multiplied by the PI. So, to be calculated, we will get our 82.5 all over the 3, and we will get our 27.5. And lastly, we have the double mass analysis. The rainfall recorded of the station X are adjusted by multiplying the recorded values of rainfall by the ratio slopes of the straight lines before and after change in environment. So example, the annual rainfall at station X and the average annual rainfall at 18 surrounding stations are given below. And later I will be showing to you the given table. And we will check the consistency of the record at the station X and determine the year in which change of regen has occurred, and state how you are going to adjust the records for the change of regen, and determine the record of the period in 1952 to 1970 for the change of regen. So we have here our given table, which we have the stations, 19 stations, and annual rainfall station X, and annual station average of 18 stations. So to calculate by using double mass analysis, well, let's say for example in 1952 and 1953, we'll be at the 30.5 plus 38.9, so we'll get 69.4, and in the cumulative annual rainfall, we will get in 1953 the 69.4 centimeter, and 18 station average we have the 22.6, which are given, and to add the given table we will have 35.5 in 1953. We'll be adding to 22.8 in the nervous station, so we'll get our 57.8. And so to solve the cumulative annual rainfall, we'll be adding the given records and the annual rainfall station and the annual station average of 18 station. To solve that, we will be just add and every year the given data. As you can see in the graphing, we have the changes in 1958, starting the 1958, and there's changes in the slopes. So we have the mean area precipitation, the arithmetic mean method, descent polygon method, and isohedral method. Arithmetic mean method, it is obtained by simply averaging arithmetically the amount of rainfall at the individual rain gauge station area. So we have the formula, the P average. We have the summation of P1 all over the N, where our P average of the depth of rainfall over the area. In the summation P1, this is the sum of rainfall amounts at individual rain gauge station, and the number of rain gauge station in the area. In the Thyssen polygon method, this method attempts to allow for non-uniform distribution of rain gauge by providing a weighting factor for each gauge. The stations are plotted in the base map and are connected by straight lines. So the formula is the P average, and where our summation of A1 is the total area of the basin. We'll be multiplying our P1. We have the example. By using the normal ratio method or the arithmetic mean method, we have the 15 stations, and the rainfall record. We'll be adding all records in the at each station, so we will get to be added this all. We have 133.1, and all over the summation of these stations, we have the 15 stations. To solve this, we will get 8.87 centimeter. So we have here the example of the Thyssen polygon method. So it says that the stations are plotted on the base map and are connected by straight lines. So as you can see in the figure, we have these perpendicular bisectors are drawn to the straight lines and journey adjustment station to form polygons, and each polygon is assumed to be influenced by the rain gauge station inside of it. So we have this example. To solve of using the formula, we will from the arithmetic mean method, we have the 133.1 centimeter multiplied by the 7,180. So by By the using formula of the Thyssen polygon method, we have 15 stations, and the rainfall recorded, which is our P1. Summation of the P1 will get the 133.1 centimeter, and the area of influence polygon, which is our A1, we will get 7,180 kilometer squared. So as you can see, the 8.8 multiplied by the 570, we will get 5,016, and so on and so forth in every stations. And by using the Thyssen polygon method, we have the P average, the summation of area influential polygon, which is our A1, multiply the P1 and all over summation of A1. So 66,740 and all over 7,180, we will get 9.30 centimeter. This is the end of my discussion. Thank you for listening, and we have the last reporter to discuss the remaining subtopics.